In this video, let's talk wiring for basic stepper-based CNC setups. This is pretty much everything you need. It is not yet on a CNC machine. So the components here are a desktop machine running LinuxCNC, the Wantai Motors 4-axis 425-ounce-inch stepper kit. That includes these 4 motors, the 4 DQ542MA drivers, 2 36-volt power supplies, the DB25 1205 breakout board, and even the parallel port cable, which is a nice touch. That was all, I think, about $250 on eBay, so a very reasonable deal. Back there is a momentary switch to act as an e-stop. That's not an ideal switch for an e-stop because it doesn't latch, but it's good enough for bench testing. Here we have a 5-volt power supply. Here is a relay that in theory would be triggering the leads to the plasma torch. And then there's also an Arduino, which is really just there for moral support. Now it is worth noting that while these components here are all Wantai brand, they are really mostly very generic. And there'll be a lot of steppers and drivers that have either similar or even identical setup and wiring. My number one tip is as you begin wiring things up, also screw them down, okay? Get yourself a piece of scrap plywood and begin fixing the boards and stuff to it. That way, when you're done, you can move the whole thing around and not cause wires to come loose. It will take a bit of time to do, but it will also save you a lot of time in the long run, not having to track down loose connections. So I used a couple of plastic standoffs I 3D printed and also made the enclosure for this 5-volt power supply. I've not yet published the object file for those, but I will clean them up and put them on Thingiverse pretty soon, and the links will be below when that happens. But if you don't have a 3D printer, again, that is totally fine. You can even just use hot glue to stick things down. In fact, that's what I did right here. If it works, it isn't stupid, right? So just do something to keep stuff in place and save yourself the headache of tracking down loose wires. As for the computer, this here is a Dell Optiplex 980. That was a top-of-the-line machine back in 2010. But even being 8 years old, it has plenty enough power for running LinuxCNC. These guys would go for $50 to $100 on eBay, so they're very affordable, and plenty of other machines will also do. I think the official requirements are to have a 1 GHz processor and 1 GB of RAM. So basically any desktop from the past decade should be fine. The more important thing is you gotta also have either a parallel port or a PCIe slot. So back here, actually, I have another Optiplex 980 because I got a deal on 3 of them. And obviously, plasma mill lathe, I will eventually need 3. So I bought these 2 in advance. So this here is your parallel port, right? Which not every machine will have nowadays, so do watch out for that. It's got 25 pins in 2 rows. It's also known as a DB25, which is why the breakout board is called a DB25 1205. If you don't have a parallel port though, but you do have a PCIe slot, like this blue one or the black one here, you can buy a $10 adapter card that will give you a parallel port here in the back. You just remove one of these plates here and the port will stick out and kind of adding more hardware. I will note that the blue and black PCIe slots are different from the white PCI slots. So PCI is like ancient stuff. PCIe has been around since I think 2004, and they've updated that one since then. So now there's PCIe version 1, 2, and 3, I believe. The only difference in the different versions, though, is the speed. So any card for a parallel port that fits in a PCIe slot will work in a version 1, 2, or 3, doesn't matter. Just be sure you either have one of these in the computer or at least one of those other slots. You might have noticed I don't have a monitor or a keyboard for this guy. That's because I actually have it set up with a Wi-Fi dongle in the back and a VNC server running on the machine. So I can connect to it from my laptop and use that as a monitor and keyboard. To be honest, I'm not 100% sure that will work long term because plasma cutters do put out a bunch of radio interference and that might mess up the Wi-Fi. But if it does work, I will do a write-up on how to set the VNC server up and configure it, and then I'll put that information in the written documentation when I get around to launching that website. But in any case, you can always use a traditional monitor, keyboard, and mouse, and that'll work just fine. I would just recommend you go and get yourself a rubber cover for your keyboard as well. That way you can keep any grinder dust or mill coolant or that kind of stuff from shorting out your keyboard. So this here is your breakout board, and it basically takes your parallel port connector and breaks it out into these screw terminals you can put wires into. You get 12 terminals here for outputs, 5 terminals up there for inputs, a couple of grounds, and connectors for your 5 volts and ground down here as well. Now this is a DB25 connector, and it splits into 12 and 5, which is why the board itself is called the DB25-1205. Right? Makes sense. See, other features are all these little black boxes here. These are opto isolators, which use light, optics, to isolate this half the board from this half the board. Basically, reducing the chance of any voltage spike making its way back up the cable to your computer frying your motherboard. Over here, you'll see these little jumpers, which connect this 5 volt and ground to this 5 volt and ground. Basically, that would let you also isolate the power provided to each side of the opto isolators. Now, I didn't bother with that because I think that's kind of overkill. I just get the jumpers in place, and I'm using those terminals there actually to feed power to the relay. Now, as for your outputs, you're going to need two terminals per stepper driver, and 1 terminal for any output like a relay. And then as for inputs, you'll need 1 pin for each kind of switch you want to have. Or you can use some configuration in LinuxCNC to actually put all of your home switches on a single pin. It just means you can only home 1 axis at a time. But I'll have to show you that more when we actually get to configuring things on the software side. As for the drivers, this is one of the DQ542MA's. I'm under the impression that anything with a 542 in the name is a knockoff of a knockoff of a knockoff, and they all work roughly the same way. So you have some low voltage signal terminals here, some dip switches for the options listed here, and then the terminals for the high voltage power to the motors. Now these switches are for the current limiting and the microstepping. If you use these drivers with the NEMA 23 425 ounce-inch motors that come with the kit, then the default maximum current limit of 3 amps is actually what you want for these motors. As for the microstepping, I currently have it set to 1600 microsteps per revolution. That may or may not actually work when I have it on a CNC machine. The only way to tell is to actually build the machine and try it and see, what can I get away with in terms of resolution without either having to go too slow or miss steps. So as for actually wiring this stuff up, the enable plus 5 volts and minus enable, the ground, are for using a digital signal to turn these drivers off and on. Basically, as long as these things are powered, they are trying to power the steppers. So I can feel these guys now are already pretty toasty because they're just sitting here actively holding themselves in place. Like I can't turn that rotor there because it's currently drawing current from the power supply to energize electromagnets that are in this thing, holding the rotor still. So yeah, you need to provide the 5 volt power to the plus enable to actually get these drivers to turn on and then have these steppers hold. But if you want to turn them off to reduce wear and tear, you can take the minus enable and then draw that to ground. Totally safe here. And you'll see the green light goes to red light. This actually stops drawing current. So I have this clamp on ammeter, which is currently drawing 0.62. It's upside down. Whoops. 0.62 amps at 36 volts DC going to this motor here. And then if I ground it, light goes red, that drops to basically 0, which just has a bit of read error. And if I had a third hand, I'd actually be able to turn that rotor around now. Of course, I only got 2 hands. So that's just what the enable thing is for. You can then use software and signals to basically turn these things off and on and reduce the amount of wear and tear they get just sitting idle, not actually doing anything. My solution is simply unplug them when I'm not using them, but you can do what you want. For the other signaling wires, you have the pulse and direction. In both cases, the minus ones go to ground and the plus ones go to output pins on the breakout board. And basically, those pins put out a signal that gets fed in air, and the driver will interpret that signal on the DIR pin as either turn one way or the other, and the signal on the pulse pin will give it the synchronization for the two sets of electromagnets in each stepper. So you see in both these cases here, I have, let's see, a blue and a green, and then that comes down to the blue and the green here. So later on in Linux CNC's Enhanced Machine Controller, I set up the step conf to tell it that the green one here is for pulse, and then it goes to pin number 2. And then likewise for the blue, and then likewise for the other low volt signals on this one here. Basically, the actual wiring you set in your software depends on what you do in reality, and any of the output pins should work equally well. With the high voltage side, you've got the terminals for your power supply, and then A plus, A minus, B plus, B minus. Those A's and B's correspond to the wires on the stepper. Now, which is which, right? Well, the thing is, it doesn't really matter so much which is which. The important thing is how they're paired. Inside here, you have 2 coils that form, electromagnets when the stepper's running. And you got to put the wires that form a coil with each other. And there's a trick to find out which is which. So you turn the rotor, and you feel, it's kind of stiff, but it does turn. And you kind of get a feel for how hard it is to turn. Then you grab 2 wires, say this blue and green, and you pinch the ends together to short them out to each other. And I'm going to hold it in my left hand, my camera hand, because believe it or not, I only have 2 hands. All right, now I try turning the rotor, and I can still turn it, which means that these are not a coil together. So I will drop the blue one and pick up the black, and now I will hold the grain to the black. And now when I try to turn the rotor, it is basically seized up, and that tells me these 2 form a coil, and that basically resists rotation of the rotor with the induced current in that coil. So that means that green and black go together, and blue and red go together. Those are actually fairly standardized colors, but it is always good to double check, especially because when you're buying from, Chinese import companies, things don't always match the standards. So it is good to double check. So here you see, I've got, red and blue here, and then black and blue here. I could just as easily have black and blue over here and red and blue over here. Doesn't actually matter. Or I can turn, red and blue around in this pair. Instead of having red be A plus, I can have blue be A plus, and then red be A minus. What that does is swapping within one pair is it actually changes the direction of travel of the stepper. So if you had the stepper turning clockwise when the machine thinks it's going in X positive, and in reality clockwise would drive your linear motion to X minus, or what you want to call X minus, you take one of these pairs, you flip them around, and then that makes it turn the other direction. Now, it's also worth noting, on most gantry tables, like a CNC plasma, you're going to have 2 motors turning in sync, but in opposite directions. So you can actually drive both those motors with 2 drivers, but off of 1 pin. So if I wanted to make these guys turn in sync, then rather than having this blue and green right here coming on separate terminals, I would just tie them to the same ones, and they would actually both turn the very same direction as they are right now. If I took these 2 wires and swapped them around, then these wires, or these motors, would turn in sync, but in opposite directions. So you see how that works? Because they both get the same signals from the 2 terminals on the breakout board. You still need 2 drivers to switch the power, because these drivers can only handle so much power. But then each driver goes to its own motor. So you can either do it that way and save yourself some pins, or you just use separate pins for each one, and to be honest, you should probably have enough pins to do that anyway. So take your pick. It's also important to notice that these power supplies from the Wantai motor kit only provide enough amps to power 2 motors at a time. So they give you 2 power supplies. Be sure you hook them up so you have 2 drivers and 2 motors on each power supply. Otherwise, you will accidentally fry your supply. Another thing to note on the supply is that there is a switch right there, that red one. If you're focused, there we go. And that's reset whether you're feeding in 120 volts or 220 volts. So be sure you set that correctly as well. This is the relay that will eventually be triggering the plasma torch in the final setup, basically acting as the trigger on a manual torch would. Now these are commodity part, you can buy them on eBay for really cheap, but I will point out the one I got is a little bit different from normal. Typically you have 5 male terminals here, and the one I ended up getting didn't have any at all. So I put these female terminals on here instead. Now the labeling on the terminals is the same, but the signaling itself is different. Okay, just another weird oddity about this relay. So you have VCC for your 5-volt reference in, your signal, your ground, and then these bottom 2 are usually jumper together. And what that does is it lets the electromagnet in this switching box be powered off the same 5-volt wire coming in here. So this switch box actually has an electromagnet that pulls it closed and a spring to push it back open. So if you don't have this jumper, then you usually have to provide another 5-volt power supply, another wire in to here. And then that will separate the power coming to this and the power coming to this, and then the opto isolator provides the rest of isolation, as we've seen on that guy there. But, you know, that's kind of extra wires and stuff, so just use the jumper, it'll be fine. Now, the weird thing is with the signaling, right? So your 5 volts and ground come to 5 volts and ground over there, that all makes sense. But the signal wire for this guy will trip the relay when you draw it low. Most of them trip when you put the signal at 5 volts. This will trip when you put it at 0. It's just backwards. So for that reason, in the next video, when I show my step conf wizard settings, when I click the invert for pin number 1, then that'll be the reason why. Just because my relay is backwards from all the other ones I've used before. I guess I just bought a different brand by mistake or something. But like I said, when it comes to wire cars and stuff, check that. When it comes to relays too, check that, right? But now it's wired up, so if I go to the enhanced machine controller and I type MO3, of course you can't see that because recording, you know, screens and all. But I hit that, then boom, it fires. And it basically takes what was normally closed and flops that open, takes it normally open and flops that closed. So now these 2 terminals here are connected when before they weren't. I type MO5, hit that one, and that shuts it off. So the important thing is you find out what will switch your relay, and you also make sure it doesn't ever mistakenly turn on for a split second when the machine starts. Okay, you don't want that, otherwise you're gonna have your plasma torch spuriously doing a little, you know, strike every time you turn the machine on, and that's just no bueno. So mess around with it a little bit. Regardless of what kind of relay you get, you can eventually figure out the wires and settings to make it work correctly. Okay. Lastly, we have the temporary e-stop here. Now this guy, as I said, is not an ideal e-stop, and it will not be what I'm using long term because it is not latching. So you hit it down, it goes down. When you let go, it comes back up. Ideally, an e-stop would latch in the down direction and have to be actively released, usually by twisting the knob or something like that. And that makes it easier to engage in an emergency and then harder to disengage by accident. Apart from that, the way this is wired also has it normally closed. Okay, so these terminals are connected right now, and when I hit the button is when they're disconnected. So I have it set up to run from an input pin through the terminals back to ground. So this is constantly syncing a few milliamps between those 2 terminals, and when that stops happening, it's interpreted as, you know, as the e-stop. That also involved hitting the invert checkbox on the step conf wizard, which again I'll show you in the next video. That's important, okay, that functionality of triggering when a connection breaks, because that means if a wire comes off, it interprets that as the e-stop being activated and it will not start the machine. You want that, okay? That's a good thing. That means you have to find the bug and actually put the wire back on before you can run your plasma. It'd be a bad thing if you had it set up so that a connected circuit is a trigger, because that way if a wire comes loose, you won't notice, okay, until 3 weeks later when you have an emergency and you hit the e-stop and it doesn't stop. So you want to set these switches up so that they will trigger when you break the connection. Same thing goes for your limit switches. In fact, these micro switches here are typically what you use for a limit switch. They make fancier ones with like longer prongs on them and stuff, but this is the gist of what you use. Again, you want to have those especially trigger when they open as opposed to when they close, because those limit switches for the gantry itself are moving around, and it's far more likely a wire will eventually work itself loose than the e-stop one, which sits off in a cabinet. Let's see. It's also important to notice that this switch here is a software e-stop. Okay, it's not really like the end-all be-all power to everything is off. Okay, when I hit that button, the enhanced machine controller here detects that. You see that the button right over here and how that flickers. That is the button to power on the machine in software or power it off. So when I depress the button, it powers it off and kind of sets it back to the default state. So it stops any pulses, it stops any program that's running. It will turn off the relay, but it doesn't actually like kill the power to these motors, right? For that, you'd have to also rig up the disable pin on here and make it work so that when you hit that button, those guys also get disabled. It's also different, from like just pulling the plugs out of the wall or having like a big old throw switch against the wall. And I would generally advise against that because that seems far more likely to eventually fry some board in here, right? You have a lot of circuits switching very fast and a lot of rather delicate electronics. Anyway, just before you actually put the thing in service, test it out. Okay, make sure you understand when it shuts off and what it shuts off, and that you also understand what remains energized when your e-stop is engaged. It's worth testing, because again, if like you set it up so the e-stop, you hit that, but your plasma doesn't turn off, that would be bad. Anyway, I think that is all for the wiring. Next, I'll show you how the software works.